We are looking at a paper titled Perceive to Reason, Decoupling Perception and Reasoning for Fine-Grained Visual Reasoning.
Yeah, it's a really fascinating one.
It is. And for the AI researchers and ML engineers tuning into this analysis on AI paper slop, here's the immediate takeaway. Vision language models currently struggle with fine-grained visual tasks in high-resolution images.
Right, the really granular stuff.
Exactly. And this paper proves that the bottleneck is not the model's reasoning capacity, but its perception, like its inability to localize small visual evidence. So to solve this, the authors introduced P2R, or Perceive to Reason.
Which is a very literal name.
Right. It's a unified framework that forces a single VLM to operate in 2 consecutive stages. First, it acts as a perceiver, outputting only bounding boxes. Then it shifts into a reasoner that uses those cropped regions to answer the user prompt.
And they train this without any bounding box data.
Yeah, that's the breakthrough. They train this decoupled pipeline without a single ground truth bounding box annotation using a novel alternating reinforcement learning strategy called PRA-GRPO. And the performance leap is massive. Their 4 billion parameter model hits 93.2% on the V-star benchmark.
Which just completely crushes the base Qwen3 VL Instruct model.
Utterly crushes it. So we're going to break down exactly how you can implement this to optimize your own models for granular visual tasks.
Yeah, so to really appreciate why a decoupled architecture is necessary, we have to look at the baseline failure modes of current VLMs.
When handling high-res inputs, right?
Exactly. The industry has generally tried to force models to look at local evidence using, well, one of 2 paradigms, and both have pretty severe scaling limitations.
Oh, for sure.
The first is known as thinking with images. This is where you basically interleave region exploration directly into the text generation process.
So the model outputs a continuous chain of thought that includes like spatial coordinates and logical deduction all at the same time.
Right. And the problem with that interleaved approach is the sheer mathematical weight it puts on the attention mechanism.
Because in a transformer, self-attention scales quadratically with sequence length.
Exactly. So when you ask a model to simultaneously scan a 4K image, generate spatial tokens, and maintain a logical train of thought, you're creating this massive, noisy context window.
The signal-to-noise ratio just plummets.
It does. And when the model ultimately outputs the wrong answer, attribution becomes a nightmare.
Yeah, I mean, you have no clear way of knowing if the error happened because the model looked at the wrong patch of pixels or, if it looked at the right patch but just made a logical error in the text generation.
Right. The entanglement of those 2 cognitive processes makes optimization incredibly unstable.
So what's the other paradigm?
The alternative is visual search methods. ZoomEye is a pretty prominent example of this.
Oh yeah, ZoomEye.
Yeah. These methods try to externalize the perception by building a complex, multi-stage pipeline.
So they take the high-res image, slice it up mathematically, run a lightweight search heuristic to score the patches, crop the best ones, and then feed those into the reasoning model.
Exactly. And while this physically separates perception from reasoning, it creates a brittle, overly complex engineering pipeline.
I mean, you've got a model in the loop operating over multiple discrete steps now.
Right. Relying on external cropping functions and routing heuristics that are, frankly, notoriously difficult to backpropagate through.
So neither thinking with images nor visual search actually optimizes the neural network for the fundamental decision of where to look.
Exactly. And that brings us to the diagnostic study the authors ran on the V-star benchmark.
Which is designed specifically to stress test fine-grained visual reasoning, right?
Yeah. They took the Qwen3 VL4B model and ran it under the standard direct chain of thought setting. It scored 81.7%.
Okay, not terrible, but
then they ran a second experiment using an oracle hint. They bypassed the model's own visual search entirely and just handed it the ground truth bounding boxes and cropped regions straight from the dataset.
And the performance shot up to 90.6%.
Right, a near 9% absolute jump on a rigid benchmark. It completely isolates the bottleneck.
It's like it proves the model already has the internal logic and world knowledge to answer the query correctly.
Yeah.
The reasoning parameters are fine.
Exactly.
I like to think of it as a genius detective who lost their glasses.
Oh, that's a good way to put it.
Yeah, I mean, you spend millions training this detective. You send it to a crime scene, which is a massive high-res image, and it has all the deductive skills to solve the case. But it literally cannot see the microscopic fingerprints on the table.
Right.
So if your response to a failed benchmark is to scale up the detective's brain by adding billions of more reasoning parameters, You're just wasting compute.
You don't need a smarter detective. You just need to hand the current detective a magnifying glass.
Okay.
And that diagnostic entirely redefines the optimization target for ML engineers. Once you isolate perception as the primary failure point, the engineering challenge shifts.
You have to figure out how to optimize the model to generate its own magnifying glass.
Without falling back into those latent heavy pipelines like ZoomEye.
So let's look at how the P2R architecture physically structures this at inference time.
Right, so they take a single VLM and strictly enforce a two-stage process. They split the forward passes into two distinct functional roles.
Stage 1 is the perceiver.
Exactly. You pass the model, the high-res image, and the user query alongside a very rigid system prompt.
And its only job is to predict 2D bounding box coordinates and assign labels, outputting everything in a strict JSON format.
Right. It does not attempt to answer the user's question at all. It acts purely as a localization engine.
And then stage 2 is the reasoner.
Yeah. You take the exact same underlying model, exact same weights, feed it the original image, but you also append the specific cropped image regions that stage 1 just defined.
The JSON output.
Right. And the system prompt shifts. It tells the model the key visual regions have been highlighted and instructs it to think step by step to generate the final answer.
Which radically cleans up the context window.
Completely. Instead of a rambling chain of thought filled with spatial hallucination, the reasoner only sees high-signal visual evidence.
The paper has some great examples of this, like the prompt asking if a vintage telephone is to the left or right of a hand lamp.
Oh yeah, the standard single-pass models get so confused by the background noise in that one.
But with P2R, the perceiver isolates just the phone and just the lamp. The reasoner gets those crops and easily maps the spatial relationship.
There's also the bicycle example.
Right. Asking for the color of a bicycle next to a kiosk in a wide street scene.
Base models get tricked by shadows and guess black. But the perceiver zooms right in on the thin metal frame.
And the reasoner confidently states it's yellow.
The cleanliness of passing structured JSON and isolated image patches is what makes it so effective. It bypasses that attention dilution we talked about earlier.
But wait, from a production engineering perspective, I hear two-stage pipeline, and I instantly think latency nightmare.
Yeah, that's the natural assumption.
If I'm deploying an API and I have to run a 4 billion parameter model twice for every user prompt, aren't I destroying my throughput?
You'd think so, but the efficiency analysis shows something counterintuitive about modern inference backends.
Okay, how so?
Well, P2R uses a single underlying VLM, shared parameters.
Yeah.
You aren't loading two separate models into VRAM, so you eliminate memory swapping overhead.
Okay. That makes sense.
And when you look at how inference engines like VLM handle KV caching, a directed two-step operation is highly optimized.
So there is a latency hit compared to a naive single-pass model.
Yes, but it is vastly more efficient than multi-stage visual search methods. ZoomEye is constantly exploring patches and running external heuristics. It can be 5x slower than a base model.
While P2R just restricts the context to a single JSON output and a fixed set of crops.
Exactly. The attention matrix computation remains tightly bounded. It's a very favorable trade-off for production.
Architecture and inference time is one thing, but, training the system seems like a massive hurdle.
It is.
Because how do you train a perceiver to output perfect bounding boxes when your training dataset doesn't have bounding box annotations?
Right. Visual reasoning datasets usually just give you an image and a text answer. They don't give you human annotated XY coordinates for every tiny object.
So you run into a severe credit assignment problem.
A classic RL issue. If you train a decoupled process using only final answer supervision, the gradient updates get incredibly muddy.
Right. If the model gets the answer wrong, was it a terrible crop by the perceiver or a perfect crop but flawed logic by the reasoner?
Updating both stages simultaneously based on a single binary reward creates total chaos in the parameter space.
So the authors solved this with an RL strategy called PRA-GRPO, Perception-Reasoning Alternating Group Relative Policy Optimization.
It's an ingenious way to generate automated supervision.
By alternating the training in discrete phases.
Yeah, exactly. In phase 1, they freeze the weights of the reasoner. The active perceiver generates a group of different bounding box rollouts for a single image.
And because the reasoner is frozen, it acts as a stable environment.
Yes. The frozen reasoner processes every bounding box rollout. If a set of coordinates lets the reasoner get the correct final answer, it gets a high reward.
So the active perceiver's policy is updated based on that.
Yeah.
The frozen half of the model literally serves as the automated reward function for the visual half.
It forces the model to bootstrap its own localization skills. Then, phase 2 reverses the dynamic.
Frees the perceiver's weights.
Right. The frozen perceiver generates one stable set of bounding boxes. The active reasoner generates a group of chain-of-thought answer rollouts based on those boxes.
And the final answer correctness updates the reasoner's policy.
By alternating, the framework continuously leapfrogs the capabilities of one role using the stability of the other,
Completely sidestepping the credit assignment problem.
without needing human-labeled bounding boxes.
Now, the paper includes a crucial ablation study on the specific RL algorithm used. They used GRPO, but tested it against DAPO, direct alignment from preferences optimization.
This is a really deep insight into reward hacking. DAPO is popular in text-based RLHF because it removes the KL divergence penalty.
Kullback-Leibler divergence. The mathematical penalty that ensures the updated policy doesn't drift too far from the pre-trained reference policy.
Exactly. In pure text reasoning, removing KL divergence can sometimes accelerate optimization by letting the model freely explore extreme logical pathways.
But in a spatial visual setting.
Removing the KL penalty causes catastrophic policy collapse.
Oh, wow. Why?
Without the penalty, the model realizes the easiest way to ensure the reasoner always has the info it needs is to cheat.
It just outputs a single massive bounding box covering the entire high-res image.
Exactly. It games the reward system and destroys the precise localization behavior.
So retaining the KL divergence in GRPO forces the perceiver to stay honest.
It ensures it continues to isolate specific features rather than defaulting to a global crop.
But this alternating mechanism raises a question about the parameter space. I mean, the perceiver and reasoner share the exact same weights.
Right. They just act differently based on the system prompt.
So isn't there a risk of interference? Like, if gradient descent makes the weights exceptional at outputting in JSON coordinates, wouldn't that degrade its ability to output fluid, logical text?
You'd mathematically assume so. But the shared parameter analysis in the paper shows profound synergistic effects instead of catastrophic forgetting.
They took a model trained exclusively as a perceiver, right?
Yeah, took those highly optimized localization weights and initialized a reasoner model with them.
And logically, the text generation should be scrambled.
But the reasoning accuracy actually improved. It jumped from a baseline of 82.4% to 83.5%. The capabilities fundamentally transfer across roles.
That's wild. And the reverse holds true as well.
Yeah, training just the reasoner improves the baseline accuracy of the perceiver.
Because it's fundamentally restructuring the underlying visual representations.
Exactly. When the perceiver learns to localize a tiny object, the shared visual encoder learns to distinguish fine edges and textures.
Which gives the reasoning head richer, higher fidelity feature vectors, making logical deduction mathematically easier.
And conversely, when the reasoner improves its logic, it teaches the shared parameters which visual features are most critical to prioritize.
And applying this paradigm yields aggressive benchmark results. Built on Qwen3 VL Instruct, the 4 billion parameter P2R model scores 93.2% on V-star.
An 11.5% absolute improvement over the standard 4B base model. It outperforms models with double or triple the parameter count just because it knows how to look at the image properly.
And dominates high-res benchmarks too, like HRBench 4K, where it gets 81.9%.
Even on MME real-world light, which is full of complex, noisy scenarios, it sees massive gains. It proves PRA-GRPO isn't just overfitting to a synthetic dataset.
It's imbued with generalized high-res spatial awareness.
The visual examples in the appendix really cement this.
Oh, the sailboat one.
Yeah. A wide, high-res photo of a sailboat far out in the ocean. The prompt asks, what animal is on the blue sail?
The base model completely hallucinates, but the perceiver perfectly isolates the tiny emblem, and the reasoner easily identifies it as a spider.
There's also the golf range example. Wide shot, distant whiteboard in the grass.
Right. What word is written on it? The perceiver crops exactly onto the board, and the reasoner reads the word elevate flawlessly.
And if you analyze the training dynamics, you see exactly how the roles interact. During perceiver training, the hit rate, whether the box isolated the target, climbed sharply.
But the critical observation is when they switch to reasoner training.
Right. The bounding box metrics don't degrade. They remain stable or even improve slightly.
And to verify the reasoner was actually using the crops and not just guessing based on the text prompt, they fed it random bounding boxes.
And reasoning performance absolutely plummets.
Which definitively proves the model relies on the visual input.
High-fidelity perception is a strict prerequisite for state-of-the-art reasoning scores.
So for the ML engineers and researchers listening, explicitly decoupling perception from reasoning offers a highly efficient, production-ready framework for any multimodal agent.
Whether you're building an agent to navigate UI elements on a 4K monitor or analyzing dense satellite imagery.
You don't need massive, slow context windows,
Yeah.
and you don't need expensive human-annotated bounding box datasets. You just need final answer supervision and PRA-GRPO.
It's a fundamental shift in dataset requirements, moving toward architectures that force the model to learn intermediate steps autonomously.
Which brings up a really interesting thought.
Yeah.
They use this to train two roles inside a single parameter space.
Right.
But imagine scaling this alternating architecture into a massive multi-agent system.
Oh, that's an incredible idea.
Right. You could instantiate a frozen critic model, acting entirely as an automated reward signal for an active actor model.
Continuously leapfrogging each other's capabilities across millions of iterations.
Exactly. Refining complex behaviors entirely without human-labeled data, bootstrapping their own understanding of the world.
We started by talking about a genius detective who lost their glasses.
And with frameworks like P2R, the AI isn't just stumbling around looking for them anymore.
No, it's learned how to manufacture a magnifying glass from scratch, completely on its own.
It's a powerful glimpse into the future of self-supervised spatial awareness, and absolutely a methodology to consider before initializing your next training run.